So, welcome everyone to our webinar, which is titled Evolution of Yelp's Data Infrastructure to Streamhouse. My name is Yanis and I work as a principal streaming architect here at Ververica. And I'm really honored today to have with me Umes. Umes, do you want to quickly also introduce yourself?
Sure. Thanks, Yanis. Hi, everyone. My name is Umesh. I'm a senior principal engineer for distributed services and systems at Yelp. And in my role, I primarily am responsible for uh, helping Yelp build, maintain, and evolve our streaming ecosystem along with the storage systems as well. And yeah, I'm really happy to be here as well, Yanis.
I'm really excited for this webinar for lots of reasons. So first of all, thank you a lot for joining us. It's also for you that are attending here. I know with all this time zone difference, this time can be a bit tricky. I mean, for me it's quite late. For Umes it's quite early. For others of you, I don't know. But I hope we can make this really interesting for you. So we're here to discuss. Yelp has been one of the first and early adopters of what we call the Streamhouse, and this is what we're going to discuss here. Before we start, I want to set the stage a little bit for all of those that don't know what is the kind of Streamhouse architecture and why it might be important and all these kind of things. And I'm going to start with this diagram here, which basically reflects pretty much how we are building modern data streaming data pipelines and streaming data architectures in general. So the thing is that typically the way this works is that on the one hand we have streaming, and this typically means in lots of organizations that we have our Kafka that basically transmits messages all over our systems. We have a stream computing engine like Apache Flink that does some kind of processing, then writes the results back to Kafka. We integrate with different databases, key value stores, and then we write the results if we want to query them into some kind of OLAP engine, right? And also these days we have vector data and vector databases. So the whole streaming landscape is pretty much in terms of integrating with lots of different systems. And this is great for streaming. On the other hand, we have the data lake house, and the data lake house is great for analytics. And at the same time, because when we have data, let's say on Kafka and Kafka topics, we we try and these days we use open table formats because also the Kafka that goes on Kafka storing all the data on Kafka is quite expensive. We offload that data into data open table formats with table formats like Iceberg, Pymon, Hoodie, Delta, right? And this is basically the ingestion part and what we call the bronze layer. Like if you're familiar with the medallion architecture, let's say you have your bronze layers here, you have your silver tables and the gold. And typically to schedule the other events, you need to schedule jobs typically on the hourly or daily interval. And for years, this is how we have been differentiating between streaming and batch. Now, if you notice on this part here, the streaming part, this is basically a kind of cap architecture, like everything is a stream. The other alternative we had was the Lambda architecture. But with this approach we have been taking also with the open table formats these days, you can see that basically it boils down to a variation of the Lambda architecture. Like on the one hand, you have streaming, then you offload the data on open table formats, but then it's a different ecosystem, it's different jobs, everything is different. And if we try and zoom in, because this approach actually looks good, uh, and this integration looks good as we see these diagrams, right? But if we zoom in practice, we can realize we need to maintain external schema registries. We have high network data transfer costs because we transmit the same payloads again and again. Because Kafka is not queryable, we need to copy the data on Flink state. We need to copy the data on some kind of follow-up system or some kind of data warehouse or indexing system or vector database. So it's data duplication is everywhere. And at the same time, we copy our data directly again on the object storage and we need to schedule jobs to recompute the same results again and again. Now, one mental model I want us to try and drive here is basically that if you think about it, we have bronze, silver, and gold tables here, right? At the same time, if you notice the streaming, there are some familiarities in the sense that you can see this part here as a bronze layer, which is basically the ingestion. You have your silver layer here because you actually enrich your data, you clean your data, you run some kind of joins or anything, which can be thought of as silver tables. And then this part here can be thought of as gold tables, right? So if in terms of subtractions, we can realize it's pretty much the same. And if you just think on the streaming part, because topics are not queryable, what about queries on real-time data? How we can query the data? Our only approach is all of databases. What about batch stream unification? Because as you can see, these are two different and separate worlds. And at the same time, if you think about it, the Kafka topic has zero business value. It's just an intermediate pipe that you just get data from point A to point B. So this got us to start thinking the way we're doing things. And if we try and change our mental model and start thinking in terms of, instead of topics, we try and start thinking in terms of tables and the table as an abstraction. We start asking ourselves how we can unify both, like have tables both on the streaming and hot layer and tables on the uh, cold and warm and cold layers and what this can introduce. So basically, there was this gap as we talk about streaming and lake houses, and there was not a good solution. Like you either had to go truly low latencies with Kafka and Flink and pay the cost of the streaming, which can be a lot, or you had the data lake houses, which was slow but provided all the analytics, and there was a gap there. And the way when Streamhouse was introduced 2 years ago was in order to fill this gap, like try and have an intermediate solution that you can do a trade-off between latency and costs and say there's things in the middle. And this is why it all started um, with Pymon as the first technology to introduce there. Basically, not just yet another table format, but basically to fill this gap to bring near real-time latencies on the data lakehouse with a table as an abstraction and be able to implement what you could typically do with Flink and Kafka, but directly on the data lakehouse. And basically, this is the complete Streamhouse stack that we have. We have the data lakehouse, we have streaming and stream processing, and Streamhouse, the intersection of both. So instead of trying to try and reason between the CAP architecture or the Lambda architecture, the Streamhouse with the table as an abstraction gives you allows this kind of new architecture. And basically at its heart for us sits Flink as the compute engine, Flink CDC for the ingestion. It all started with Apache Pymon, and I want to keep it Pymon focused for now to not confuse you with lots of technologies, but we'll also discuss Apache Flux later. And basically, this was the starting point, and the use cases that Pymon tried to address, and this kind of the first days, let's say, in the Streamhouse when it was introduced, was to provide large-scale change data capture. So basically, you have Kafka, you have your database, and you can just in really with really high throughput and low latencies, and of course costs ingest your data into your data lakehouse. Then it was about replacing Kafka as a message queue directly on the data lakehouse. So if you can afford some extra latencies, this can be an approach you can also look into. And I think there was also some benchmarks I had seen from when New Relic was trying it out that they achieved end-to-end 8-second latency with Pymon. Then it's about streaming materialized views, and I have the use cases below, and it's also fast rollups, which basically means with Pymon you also have this trade-off that you can use. If you can trade off some writes by using deletion vectors, you get some small extra latency, but you get really fast rollup queries. So it's also about really fast rollup. I think the numbers I have were around 4 or 5 seconds rollup. And the streaming materialized view can be thought for basically creating tables that continuously get updated, and you can get out of the box event ordering, duplication, multi-stream merging when you have multiple streams instead of running large-scale self joins, does just do the merging cheap and efficiently onto the data lakehouse, streaming aggregations, and of course streaming data enrichment. And I just wanted to provide a really quick overview and now pass the ball to Mesh for the main thing here. To sell Yelp's did basically Yelp's bet on this Streamhouse concept, and I want to highlight here that Umesh and Yelp were from the first adopters that really understand the value of this architecture and took a leap of faith there, and how they contributed lots of things from Flink CDC to complex event data types in Pymon to integrations with AWS and Amazon Athena. What I mean, you did so many things, man. So
All
I
right,
mean the details. So yeah, passing the ball to you now.
thanks. So yeah, let's take a overview of the system first. So essentially, the slide that you showed earlier on, I would like to start with the overview of how our data infrastructure landscape looks like. And typically, data flows from left to right in this picture. So on the far left is the sources. So at Yelp, as I guess is at most places, all of the data essentially originates as a stream. And I personally think of these as like two high-level categories of streams. One is the change data capture from databases, uh, which has very different characteristics and requirements. So we need to capture database change log. For example, a new review was written, or a new photo was added, or likes, and then this has to be copied all the way over to other derived indexes like search indexes, because we have support those stores. So that's the change that I capture, which needs to flow through the system. And then we have MySQL like relational databases, and we have like key value stores like Cassandra, which emit these kind of events. And then the other type of category of streams that are emitted are your typical log events, um, application logs. So again, this can further be classified as, they could be operational logs, which are just useful for our infrastructure to have observability and metrics on them, gives an insight into the health of the system. But there's also could be service logs, which are like more domain specific, which could be used in one of two ways: either directly as a feedback for product, with things like the consumer interaction with certain pages and those things. On the other hand, it could also be used in a more analytical way to have further data, like run machine learning jobs and whatnot, to have further signals for like, hey, which features can we drive on search, etc. But at a high level, uh, on the very left, it's essentially other streams, change data capture streams, or they are event logs. That's the takeaway. And then what we did here was, we back in 20, I might be wrong on the year, but 2014 or 15-ish, we were one of the early adopters of like, hey, let's adopt to like streaming first. So Yelp exists even before that, and we solve these problems in various ways. Use a bunch of other technologies which I'll mention. So, but we said let's consume everything as a stream, which overall is generally a good idea. But then we need to have some definitions around how we consume these streams. So we came up with a data mesh architecture, which means the ingestion layer is a Kafka. So all these events are captured, or streams are captured in Kafka, but they have to have a schema, and the schema is uh, written in a schematizer, and we use Avro as a protocol for the wire. And this schematizer again was basically a custom in-house application that we built. So every Kafka, so we didn't deal, like the streams were not dealt at the level of Kafka topics. They were dealt at a higher level of abstraction called streams. And every stream had a schema, and you could go look at, given the ID, you could look at the schema in a schematizer. So that's a general idea. Um, that's the ingestion and transport layer. And then the next one is the query transformation layer. Again, as Jan showed, it's very rare that you just get the raw data and like, okay, just put it in the OLAP, or in our case also in an online store, like I said before, for search. But there is often times multiple jobs that will be run to get derived signals. So you can think of these as loops from Kafka to Flink to Kafka. Again, like Flink is our compute engine that we use for the most part. And back in the day, we either had, again, the abstraction for the users of this data infrastructure at Yelp, which is other developers of feature teams. They could either use SQL, like the Flink SQL, which we adopted to more recently in the past couple of years. But before that, they could just write plain Jane, JVM, apps in Scala or Java, whatever, to do their data processing, filtering. And some of the key features we needed, especially on the CDC side of things. So for example, if you're getting data from reviews and photos and users, tables, then we need to do the correct joins, the correct ordering, and these can be unwindowed joins. So sometimes the state can be very, very large. And we have to not only maintain, so what we had to do was use Kafka topics, compacted Kafka topics with keys, which means all of our database, let's say it had a very high cardinality, that had to be maintained in Kafka. Although Kafka compaction helped remove the old stale entries, we still had potentially, because at any point, any new team can come up and they say, I want to consume all of reviews, then they would go to the Kafka stream to consume that, and that would have very high cardinality because that's your storage. So we kind of use Kafka as storage, hence Kafka goes there as well. And they could write their own apps, and then they could do these joins across various streams, producing more outputs. And this problem is kind of exacerbated recently with vector embeddings. Because from what I've seen in practice is vector embeddings typically for higher dimensionality takes up a lot of space. So now you can imagine there's a very cost storage-wise long stream. You join with, let's say, a stream which has maybe a couple of floats, but you produce a third stream now, which is it's going to take the size of the longer stream. And then you have these duplicates that Yanis was mentioning earlier. And then eventually, after a bunch of these cycles, we would either put the data in online stores, like I mentioned before, which is search, Cassandra to name a few, or we would go into the typical offline stores. So now we also have a lot of history on the offline stores we use. We used to have legacy data warehouses, and then we tried to move to data lake a few years ago. But our data lake, the initial form at least, was pretty low level in that we had data as Parquet in Parquet format on S3. So the storage was S3 and the data was in Parquet format. And then the one thing, and then of course, once the data is in the data lake, there can be further batch processing on this using various other technologies that we have. To mention a few, we use Spark typically for running some of the machine learning jobs or insights on this, like I mentioned before, or we use dbt more lately. And also these offline stores, the data lake could be used by other dashboards and notebooks and product analytics directly. Uh, the one thing I'll say here is uh, the use of connectors. So I'll quickly talk about what connectors are. Connectors are in essence essentially your entry points and egress points into your data streaming mesh. So how do you get data from MySQL source or let's say Cassandra source or a log event? Like that's your connector. Uh, so for a log event is typically you just have a library in the client which routes it somehow to the right Kafka topic with the stream schema. But for the data stores, which has the CDC nature, we wrote our custom Flink applications, which are connectors, which would run things like for MySQL, we would run the Bezium core engine because there's a lot of complications in that. We need exactly once delivery guarantees, and we need ordering, and we did all those things. And on the other side, we also have the sync connectors, which is how do you take data out of the streaming ecosystem? Because once it has to land in um, the bats, like the offline stores or the data lakes and data warehouses, um, it's basically out of the streaming system. So we had connectors, and we saw a lot of stability, kind of reliability issues in this. So as you can see, the business impact is huge. If somewhere upstream, one of the Kafka streams was delayed, or the Kafka disk was getting too full, or the client was, back pressured, or the Flink jobs often were back pressured with state, then it could have an impact somewhere very further down the stream that a financial dashboard is being delayed, right? And then that's a pretty severe impact. So it put a lot of strain on our engineers and overall, the operability of the system started suffering. Not inherently because the architecture is bad or anything, but we were limited by the technologies then. And the growth of the business, and we just had an explosion of all these. Because one thing was we kind of were victim of our own success. Like teams would push, let's say, a config file with streams, and then automatically the Kafka topics would get created, and the streams would be routed, and the schema would be created. Schema evolution is one more challenge that I guess we can talk about. often teams would want to evolve schemas, and you have to play by some very strict rules. And I guess the easiest way generally would handle this is adding columns is fine, but like removing something is not fine because then you have these mismatches. And Flink SQL kind of makes it harder with the table environment in Flink SQL. I believe when you have the SQL change, the state is incompatible with the old state and the new state. The job would not start. And oftentimes, then the only option is like, do we throw away the state and do we continue from some checkpoint or do we go all the way back? Now that depends on the use case where some cases like the feature teams were like, no, you cannot throw away the state. So these things become more complicated. But yeah, another thing I'll mention is the connectors were, apart from being not very reliable, they were also, especially the sync connectors, they were very slow. It would have in order of hours of latency for various reasons, like we had to pull the data from a stream, which is continuous at a boundary of a day level, and then for every day we would index the data into the offline store and kind of these restrictions. So having spoken of this, Yanis, you want to go to the next slide?
I had this question whether I should change the slide or not.
Yeah, no worries.
Just
So
tell me.
I,
Just
I
tell me
spoke
what
I spoke a lot about like the just what we had, but again I'll echo on the second point here, which Yanis was mentioning. If you see, largely there's a disjoint ecosystem for streaming and batch, right? Like I said, storage for streaming was essentially Kafka with at times infinite retention. Compute was Flink, and the serialization format was Avro. Now, if you go on the batch ecosystem, the storage is S3, the serialization format was Parquet, and the compute was for the most part Spark, but we also had Athena and other things. And as you saw, like yeah, the complexity or the number of Kafka touch points. Um, so you really generally want high availability, but the more number of hops you have in a system, even if individual component is fairly highly available, the overall availability goes down, and that's where we started to suffer. And yeah, I also mentioned the cost issue. Yeah, we can go on the next slide. So, I mean, given all this, I mean, the target architecture writes itself fairly like, it's basically what I was explaining, that we need increased reliability for sure. And when I say reliability, specifically what I mean by that is we need increased availability, yes, but we also need a lower mean time to recovery. There were two issues with this. One was we had these implicit directed acyclic graphs or chains of Kafka Flink from all the way from a database to some endpoint. And if something failed, it would be very hard to like figure out the impact because of lack of lineage or governance in general. And then even if you figured that out, replaying it would be hard because we had to go almost like from back to front. So the MTTR problem we wanted to solve for the most part. Debuggability also, I think Yanis talked about, like Kafka is generally an append-only log. So you have a few ways to debug, like when things are suspicious. One is use Flink SQL. It's not like the easiest to iterate on. Or the other one is what the developers typically did at a practical basis was we would write a new connector to get the final Kafka topic into a data lake. And then we use our trusted tools like SQL or Athena or dbt to do entire parsing of the data. But as you can see, this is pretty heavy-handed. It's not very iterative. Yeah, cost we talked about. Data freshness I did mention for the analytics stores, the connectors. It would be really nice to see your data in the analytics store in order of single-digit minutes, maybe, not hours. Complexity we talked about. And there is like when developing the systems at a company of scale, Yelp, which is already infrastructure really like a means to an end. It is powering some business use cases. So kind of an implicit mandate is you need to continue supporting existing systems, and the feature teams will continue to add new streams or new things, but you somehow have to move the infrastructure to a newer, simpler, scalable ecosystem. And you have to minimize the business disruption and execute fast. So that kind of also dictates like what are your alternatives or options uh, to go from here. I think, yeah, we can go on the next slide. So this is mostly how our architecture now looks like. The first things first, like you can see, it's fewer boxes, so it's more simplified. Um, so again, on the far left, we still have the database source as CDC, but we stumbled upon Flink CDC, and we realized like, oh, we don't really need to maintain our own connectors, which put the data into Kafka, and then from Kafka into Streamhouse, we can simply reuse the kind of Flink CDC source connector from MySQL to Pymon. And at the time we started working on this, I think it was still Flink CDC and the Pymon connector even. And I thank Yanis, like I would ping him like, hey, is the Pymon connector ready? And he would say like, yeah, talk to these people. And then we would go about our business doing that. And the other thing was we wanted support for complex nested objects because our schemas, we like I said, we already supported schematized data mesh, so our schemas were fairly gnarly with like deeply nested objects and complex data types. So we added that support. And one shout out I want to give is the Flink, both the Flink CDC and the Pymon community have been like really good with iterating with us and helping us like okay merge our PR so we can continue to use the upstream main branch. Otherwise, it becomes a chore to have your own patches and maintain them. So Flink CDC helped out here, simplified things. For the application level stuff, what we did was we realized again Pymon when I started working on this I think a couple of years ago to do a quick POC. One of the challenges was since we had our own streams in our own format and our own conflict registry, I could not just inject them into Pymon. I had to convert them into something Pymon can ingest into. And Pymon at the time had just released a Kafka CDC, and there was a PR in flight for the Confluent schema registry support. And again, I worked with the developers, and they got it in no time, in a matter of weeks, I think. So then my adapter would just convert our custom schematized streams to a stream another Kafka topic, which is easily consumable by the Kafka series in Pymon. So again, so no work for us. We just have to do the conversion. So now then what we have done is we basically emit streams in the new system in the it's still a Debezium format, but the schema is in the schema Confluent schema registry. We don't need to maintain our own at this point for these new streams. And then Pymon, Kafka CDC takes over from there. So you can see those arrows, they go into Pymon. So once the data is in Pymon, now that's your storage. So you can see on the right side as well, the storage is Pymon. Again, we cut off Kafka at that point. So what this now lets us do is we don't really need those long TTLs or infinite retention on Kafka, which doubles up as a database. Folks just subscribe to Pymon because Pymon has these nice properties like snapshots and tagging and all those things too, with the merge engines, which I'll talk about later. So once the data is in Pymon, now our go-to or de facto is still Flink SQL because a lot of our earlier code, the user configs were in SQL. So moving that over to this is not too hard because it's the same language. And then for the more complex use cases, we choose to use UDFs. But now the loops from Kafka, or the chains from Kafka to Flink to Kafka are reduced to Pymon to Flink SQL / UDF to Pymon. And then we did have to write a couple connectors to get the data out of Pymon into the search store and also into the Cassandra sync. So we had a couple of sync connectors there. Then the other big thing, or the big win, in my opinion anyway, was bridging the gap between batch and streaming comes, is next. So essentially, we don't want to disrupt remember the minimum business disruption mandate that we had? We can't ask all our dashboards and users and dbt and Spark jobs to now start querying like something else. So again, we worked with the Pymon community because essentially we knew that the data formats were the same as respect to Iceberg, and we were already thinking of moving to Iceberg. There's a whole team at Yelp dedicated to moving our analytics store or aggregating all our data warehouses and old data lakes to Iceberg. And Pymon has this nice feature of the compatibility feature, which is basically your data is still in Pymon. You only ingest it once, but you turn on this Iceberg metadata compatibility, and we can have our metadata also be stored in a format that any Iceberg clients can read. For example, a Spark client or a DBT client should be able to read that Pymon data as Iceberg data, given that the metadata option is stored in the format. And I think at the time Pymon supported Hive and local, and we wanted our metadata to be in AWS Glue. So again, I think our developers worked fairly quickly with the Pymon community to get that feature supported. So that saves us another hop or another cost of data storage. And remember how I was talking about the connector as delays of hours? There is no such delay now because there is no connector. Essentially, if you say, for example, I have to take my data from a database into Iceberg, all I have to do is launch a Flink CDC job into Pymon. The table, we have to say Iceberg compatibility mode on. So now I have a Pymon table which can be doubled up as an Iceberg, and you can immediately, folks using your old tools to query Iceberg data lake can still do that to query that. This also solves our somewhat debuggability problem when we launch new streams and feature developers want to see the data sanity. They can use this as well. So this is pretty cool in my opinion. Anyway, yes, Yanis, you go next. I think I spoke all. Yeah, maybe I'll talk about so the complexity I've talked a lot about. You can see the unifying. Um, Now the storage essentially is Pymon. That's where the data lives. And the compute, we still have Flink and Spark as a primary compute. And then if you want to count like the Athena slash also DBT models, they're also in a way compute. Um, and yeah, we talked about the costs. Um, yeah, I did talk about the live Iceberg tables as well. So these are some of the nice properties. And honestly, like I started to me fairly like I would have said like this is a success if you're even able like the goal was to make streaming consolidated. But the
Mhm.
benefits we got just by doing that on the batch side of things also, and how it helped out adjacent things like connector, it simplified the whole connector ecosystem. It simplified our batch systems or the analytics store systems. That was kind of a nice bonus, I would say, which kind of makes me believe more in the unification of stream and batch. Yeah.
And I think this is one really important thing to highlight here, and the message that we need to also get to more people. Like when we actually talk about streaming first, because I'm also one of the first people that always advocate for streaming first and streaming native. It doesn't mean streaming all the way. It means start with streaming because at the end of the day, a stream is a never-ending flow of events, and a batch is just a snapshot at some point in time. So if we try and adopt this metal model, yes, it's streaming first, but it doesn't mean compromising historical context or batch. And this is what I also see as the foundation we need for all the modern ML and AI systems. And if we start going down the direction and treat these things with the same abstraction, I think the benefits, as you mentioned, can be really, really interesting. And I have some questions for you. The first one is, as you mentioned, and this is also one thing that is also worth mentioning, is that more, I think at least four out of the five use cases I would say with Pymon, Iceberg is always included there. So people use Pymon along with Iceberg with the Iceberg compatibility. But since you were one of the first adopters, when Yelp started going that direction, did you hear anyone say like, "Why Pymon? Why not Iceberg?" And how did Yelp? I mean, what happened there? What's the story behind that?
Yes. So we did get a lot of that. Like I said, essentially analytics or kind of like the infrastructure side of analytics or like Iceberg feeds our business for like the analytics side of things, and which is very like batch oriented. And in the streaming side, we were trying to fix our cost, reliability, operability issues. Uh, and then when I came across Pymon, I started realizing quietly, like, okay, this is actually going to solve some of the issues they're having to. And we had basically a team focusing on moving to Iceberg at the time. because our data lake itself story was kind of messed up in that we had legacy data warehouses, and then we were trying to move to data lake, but the data lake was just Parquet files, and we had a lot of state and other things to manage. So I did get a question like, "Hey, Paimon seems like a lake house, right? Why don't you choose Iceberg instead? Because we already kind of plan to have it." And wouldn't have been an problem for me, but like I said, I was trying to solve the streaming first problems. So the nice thing about Paimon was it was born out of, I believe, the Flink table store, which is how I got to know about it. And we were having issues with we had to support things like CDC, change data capture, ordering. So today, like when we turn on our table in Paimon and I say I want change data log capture, CDC, we for those things we don't say none, we say whatever the format is we want it. So that's something like streaming first was not inbuilt in Iceberg, right? Or things like unwindowed joins. Like I said, we want to get we essentially in search index, you can think of the search index as a document or a materialized view, and our data is streams, reviews with users, with photos, with whatever. So when we do these joins, we might have to look back in an unwindowed join way. So that's the other thing we wanted, which is again a streaming first construct. Ordering
Okay.
guarantees, like you can't have things be in search index which are deleted, being overwritten by something new. So all these things are streaming first constructs. So that why, like for the streaming part of things, my opinion was okay. It's a no go. Like we can't just use Iceberg to solve these things. And then the nice thing of Paimon happened in that because I think it's what's the word I'm looking for? It's inspired so much or like uses so much of the core of similarities of the formats and stuff from Iceberg. The Iceberg, the metadata compatibility feature that really works out well for us. Otherwise, we'd had to write a connector to get data into Iceberg because since the teams like we had a data lake and we were committed to using Iceberg, the abstractions and the query layers, we didn't want to break that. So, which is why I say it's a unifying, but it's in a neat way in that we kind of have the best of both worlds, really, if I can say that. Like where if we solve the streaming problems with Paimon, we turn on the metadata compatibility feature. Now, I mean, it's of course like not all bells and roses. There are certain things uh, in the compatibility layer we can work on and features we can improve, like the compaction support and whatnot. But it's a big win. Like just a whole class of problems goes away. We're like, okay, data is in Paimon. Now, if you want to use it as iceberg, use it as iceberg. But the other way around, we cannot do. Like we cannot say, oh, data is an iceberg, but now also use it as a stream. That doesn't happen. So,
And
so yeah.
I want to highlight that because I see often lots of people coming in the Flink mailing list and asking about solutions like for Flink and Iceberg and streaming and change data capture and schema evolution. I'm like, just use Paimon and use the compatibility. It just works. Like, yes, you need to ask the question before go down that route. Technology is great, but you need to ask the question first. What problem am I trying to solve? And does technology solve it first? I mean, I see companies just trying to solve issues that are already solved. They throw lots of engineering effort, and at the end of the day, the end result, even if they achieve it, will not be the same and the desirable. So it's like going in such a big marathon and climbing a large hill for something that is already there for you. And the other thing I want to ask you before I go into more now to introduce the next day about the Streamhouse, about the reduced cost. Most of the use case I have seen, basically every company has different ways of measuring cost and they try to measure different things. Like some just measure on the ingestion layer how much they saved compared to another, for example, table format. Others share about how they saved in the total storage costs. Other in computer resources, for example, from moving from Kafka to Flink and Paimon. But the thing I see there is that everything is always between 50 and 80% cost savings, which is huge. Is this something that you also saw there?
Yeah, I would say that. I think we said that in our blog post too that we released with AWS, where essentially it's, of course, the S3 storage costs are always way cheaper, which is what we use Paimon Backpack compared to the Kafka. But it's also the network costs, right? Like when we have self-hosted brokers and whatnot, the data copying and all that also is gone, comes and you get the availability of S3 as well. So I would say it's definitely that, and because you got to know, like in the graph of the pipeline that we have, how many copies of data exist. Like there's a lot of copies of data. Like I said, especially with vector embeddings. So if you go like job by job, for the jobs that are really the ones with compacted Kafka topics, we would have infinite retention. So we had, like I said, we would have entire databases. Now those are just essentially going away in the Kafka detail itself is like very little for, I mean, actually we don't even have it for a lot of them, but for S3 it's very little. So I would say it's in order of, yeah, you're right in the ballpark there, 50 to 80%. And it's not only what we're doing now, but how it scales in the future. Like now we are just seeing in the last 1 year or 18 months, more and more teams wanting to use vector embeddings. So it's just going to scale much more linearly than otherwise it would have.
Yeah, and I think this is just the beginning, and I will expand on that now that I'm moving on the next one. But let's keep this data duplication in mind as we introduce now and see. Basically, as I said, this is how the Streamhouse concept started, like with Paimon, and tried to introduce a sweet spot between the lake house and streaming, and basically what we saw as the next step and the next evolution for streaming. Now, how Apache Flux completes the
So
streaming?
Yanis, yeah, before you go into that, a quick question. So we
Mhm.
use the default, pretty much default Paimon settings, and we get minute level latencies. Like we have tested it for like 2, 3 minutes. I've seen and heard about New Relic using it
One
in
thing to
sec.
clarify, here that I want to ask, is this about the primary key tables or the append-only tables?
Um, I would say it would be nice for both, but I think it's primarily for the former, the primary key.
Yep.
Because like let's say there is a new, I mean at Yelp if you're doing a reservation or a booking, then if a database change happens, we want to see it in the search index as fast as possible. So sometimes we still have requests for like, hey, could this be done in order of seconds? Um, so yeah, I don't know. That's the only
So
thing.
the latency for the primary key table are typically to the minute level. For the log table, because it also doesn't deal with updates, and actually it's just that doesn't deal with small files. Basically, more appropriate, let's say, and easy to handle on the append table, you can achieve lower latencies. But for the primary key tables, the latencies are there. And this is why also Apache Flux also comes to complete this picture for the low level latency, because even though we introduced the Streamhouse, we didn't have a way to achieve low level latencies. And this is the filling gap that Flux tries to complete. So basically, Flux is like for the hot layer, similar to Kafka is, but by rethinking streams as tables and not topics. So basically, we try to think like, okay, in an ideal world, we want to have all the different properties we have of streaming, but at the same time, from the lakehouse and data warehousing world, we get all these cool properties. Like we are able, because it's columnar storage for the most part, we can do predicate push down, we can do partition pruning and column pruning. And these are great for also minimizing the network transfer costs. At the same time, what will happen if we could also have a key value store in between? So by merging all these different properties, the result of all this work, and by having the tables and abstraction that can support all these things, we have Apache Flux. And basically with Apache Flux, we have the cluster, and we have all the data sources, like we have the Kafka, you do the ingestion of Flux, but now you don't only have a log table, which basically provides the same functionality like Kafka, but compared to Kafka, the log table is based on Apache Arrow, the columnar format, which allows to actually query that directly and provide columnar properties and capabilities. Now you also get a primary key table, and the primary key table also has, it acts similar to a database and has two properties. It still has a log store similar to the log table, but also has a key value store. It's like a database in the sense you have your primary key table with the latest changes, but behind it, it's being supported by the write ahead log that keeps track of every every change that takes place on your database, which is also really important and crucial for auditing, right? And consumption and all these things. Now, the other interesting thing with Flux is that it provides a direct, unified batch and streaming architecture with a lakehouse at its core, because all the hot data and the real-time data live on Flux tables, and the cold data gets tiered on open table formats directly on the data lakehouse, and it syncs the data automatically through the tiering service, and also syncs all the properties like bucketing and partitioning. So it supports right now Iceberg, Pymon, and Lance. So it solves all the data freshness issues, all the update issues we'll see in the next slide. It also allows you to query only the data you need. So for example, if you want to do a streaming read, right? Let's assume you want to do a simple filtering from a streaming job. You need to consume all the data and transmit them over the network. But even though you might need only a small portion, you have to pay that cost. With Flux, you can just add the filtering condition and only need on the storage layer, the server sends all the related data there. And this goes back to the whole stream and batch unification, because as you can see here, it's again like having the bronze, silver, and gold layers as we talked in the first slide, and you have data flowing. The data flows on the hot layer. You can do anything you want, and you can store key value data for lookups, right? You can store columnar data that are great for rates queries and aggregations. You can store also vector data. So you have a single play. You can think of Flu similar to Iceberg in the sense that it's real-time hot shared storage, and then you can also add query engine on top. Like right now, it supports Flink. The next release brings Spark and Trin integrations, and early next year, I think it's planned for Starox integration. And then it's basically it's what I see as the essence of stream and batch unification, like one unified view, one table, one SQL statement. You don't have to differentiate between batch and streaming. One table is basically this whole thing can be thought as a whole table where the whole data lives on Flux, warm and cold data lives directly on the data lake house. You basically have one table and you play with different freshness layers, and you can run queries that combine the data from both historical and real-time data. And the same goes for the SQL execution, because it's also based on Flink that has the same exact engine that just works on batch and streaming data. It's about execution modes. One is bounded, the other is unbounded. And in the long run, I think this is going to unlock really powerful benefits for for the enterprise and the overall architecture. So it's technologies, but the core principles and the philosophy for stream batch unification is the most important things I would say. And if anyone is interested that is seeing us and wants to get into more detail on Flux, there's a presentation I have online. It's both on the Ververica YouTube and the Flink Forward one. It's called the Seven Deadly Sins of Streaming. So if you're interested to find out more, just go and check it out. And yeah, I mean, I don't know. There at Yelp, have you looked into Flux? Have you thought about it? Or if you have heard about Flux, what are your thoughts around it?
Yes, I have looked at it, and we have a couple of people, engineers, who have played with this, I think, during the hackathon. And this is something on potentially on our radar, like for certain use cases, which do warrant, sub-minute, whatever, few second latency. Um, right now, we don't have many of those, but I'm sure like it's already people have already been asking for it. The key for me is now that we are on Pymon, let's say we're using compute is mostly Flink, we are in Pymon. What would be the first, according to you, base easy uh, barrier to entry step? What would be the next step? Like, let's say I have a workload using Flink and SQL on Pymon, and I want to now migrate this to Apache Flux. How would you go about
That's
that?
that's a great question, because I also saw this next week. So the Pymon community introduced a new proposal that they're working on to basically, actually, let me find it. Let me try and find this out. It's about compatibility of Pymon with Flu. So I think it's pip. Um, so it's this proposal here, enabling place upgrade of existing Pymon tables for some second latency for Flus. So
Mm.
it's a way in the proposal to just go from Pymon to Flus for easy migration, because this is a great question you just raised there.
Right. So that might be our go-to then. Like, hey, like these Pymon tables, we need freshness, you know, much sooner.
Yeah.
I just okay,
I need
cool.
to ask around in which release is going to be included, but I think it's going to. Okay, this is from Yuxia, so I assume this will go really fast into Paimon. Yeah, because I
Cool.
think that there is lots of requests around because there are lots of users. I think some that come in mind right now. I think there are Lala Move by Dancing TikTok that already, and maybe Xiaomi. I don't remember. I need to check. That already have Paimon tables and they are looking into Flux. So these kind of companies would benefit from it. Um, what
Uh,
else? Yeah.
Yanis, I think we have a few questions in the chat.
Exactly. Yeah, I just want to say that I think this was all from us, and thank you everyone for bearing with us and listening to us. So let's see what questions we have. If
I
on,
think a lot of them are for me, so maybe I'll start answering them. So the
okay,
first one is from George
yeah.
Leonard. I'll just repeat the question so it's on the recording as well. Considering you wanted to get to real-time streaming, which use Spark, which even at the smallest is still a batch-based architecture, why not move everything onto a stream architecture on Flink? Yeah, I mean, in theory, this is totally doable. But like I said before, one of our mandates is minimum business disruption. We have hundreds, maybe if not thousands, of workloads on Spark. So we could, in theory, move them to Flink. But what we're getting out, the bang for buck is now Spark in the past used to query data lake, and it used to also like the Spark RDDs and whatnot were built over data lake, and they were also built over Kafka. Now it's simple. The Spark client can simply use the Iceberg client lib, but the data is just in Pymon because the tables, like as I mentioned, have Iceberg compatibility. So we kind of have like most of the benefits of like the data is already available in Pymon with a fairly fresh, like a a low or a more fresh, like a low latency, and we can continue to use the import like so that way we don't have to break the interface and go talk to all the teams like the ML infrastructure team and the Spark users and the data scientists to use this. Um, So what's the next question? I guess that answers that. What are Yelp's latest requirements? How fresh is your data? 1 second, 1 minute, 1 hour. Did you notice increase in throughput in stream processing by adopting Fluss Pymon? So I think we spoke about this. The latency requirements typically are few, I would say single digit minutes, and we meet them. There are a few cases which we might want to move. We have other mechanisms to do like a typical message queue and kind of stuff for lower latency, or we just go synchronous as well. But Fluss might be something we could look at for this sub-minute level latency. And honestly, we have not even tried to optimize a lot of the Pymon configs. So we could do that as well as a first option. Did we notice increase in throughput in stream processing? So like I mentioned before, end to end, we just reduced the number of hops from Kafka to Flink to Kafka and all the Flink state issues we were having. So the end to end from a point that data is emitted into the system to the time it gets into, let's say, analytics store was hours, or if it goes into search stores was a few minutes. Just by removing a lot of the hops, we definitely have improved the latency, but also the capacity to do the more work, which is the throughput. What's the next one? How was the experience with auto scaling in Pymon? So I don't necessarily know what you mean by auto scaling in Pymon because the way we run our systems, we have self-hosted Flink and we deploy our Flink in Kubernetes. So Kubernetes pods themselves are auto-scaled based on compute and other things. We have our own Flink Kubernetes operator. And Pymon, the data itself is on S3. So as the jobs have compute pressure, or we need more task managers, we bring up But Pymon isn't necessarily the bottleneck in autoscaling. It used to be either the back pressure in the jobs due to slow processing and those things. Um, yeah. The other nice thing I would like to say is some of the constructs that we get out of Pymon, like the partial update merge engine. Like doing n-way joins is really annoying. If you have used Flink and RocksDB and those states, it can get really painful if you're a developer because like there is some retrospection into state, but not much. But the partial update engine is really nice that we have this property where we have a materialized view again, like, and then we can
Mm.
just have different jobs seeding to different fields and yet maintain the ordering and those things.
So actually, as one thing, and I will share it in the Slack, I wrote, and this is something that applies for both Pymon and Flux, is how with Flink they introduce what I call the era. Actually, it's more than just joins, it's compute store separation for joins, aggregation, and this kind of operations. When you work with Pymon and Flink, or Flux and Flink, all the state tag can actually be offloaded to the streaming storage, whether it's Pymon or Flink. So if you have issues with large states, this is also something to look into, and you can find more about this in the Ververica blog post here, the introducing the era of zero state streaming joins. But it's also in my presentation, the psychedelic scenes of streaming. Yeah.
Thanks. I'll keep reading the question. In this architecture, how did you ensure offline online store skew drift? Why not Pymon tables to be the source of online stores? So the store drift, so the requirements are somewhat different. Like we have dedicated online stores, like search. For search, we use Lucene based database. We have our own open source NRT search, which is based on Lucene. So that one has to be used. We can't really use Pymon unless we start supporting Lucene indexes in Pymon or something of this sort. So we have to get the data out. And the skewed, like I said, the business requirements of the offline stores are very different from the online. The offline stores, the analytics stores, the users are trained to think like it's hour level latency or even like days, and they even the partition key is generally by date or date, whereas online have very different requirements. So this wasn't necessarily as long as the online were always caught up with the from the time a reservation happened, or like I don't know, a booking was made or a review was written, to the time it is searchable or a click was done. That was the key. The offline stores now because of Pymon, in fact, it's much better. Are there any other questions?
Yes, there is another one in the end from Ahmed. If you're not yet very invested in Pymon or Iceberg, but need sub-minute latencies, would you invest directly in Flux? What do you think maintaining Apache Flux cluster? What? I don't think I get the second part, but for the first one, just getting your opinion, I can also share mine.
Oh, just my opinion. So at this point, we are invested in Pymon. So
Yeah, so
that's why I asked you, like, how do I get some workloads into Flux? But I mean, correct me if I'm wrong, Yanis. Even if I were to invest in Flux, I still need a core layer, right? Why would I pick something other than like? Is there a reason to not pick Pymon as
exactly.
that?
So here's the thing. There is the way I would approach these questions is would you invest directly in Flux? Like the first question is, are you about to build streaming data platforms? And is this streaming data platform that needs to deliver no like low latencies, it needs to power lots of business critical analytics for the business, all these kind of things. If the question is if the answer is yes, then you definitely should look into Flux. Now if you haven't invested in Pymon or Iceberg yet, it's not that you have to, like, you don't have to use the tiering service and offload there. You can just leverage the tier storage if you want. But if you're creating a streaming data platform, at the end of the day, you will need historical data and unified batch streaming, right? So it only makes sense at some point to also invest into the table format. And as I said, Flux supports both Pymon and Iceberg. The lens data format is there. So if you also want to store vectors and integrate with things like LanceDB and do vector search. You also have this option. So basically, Flux doesn't force you to something. It allows openness. It's up to you to decide how you want to run things. As I said, the core thing here is the table as an abstraction to just allow you this meta model to allow you to think in terms of unified batch streaming architectures because, and this is something I'm advocating a lot for, is that I don't think you can achieve true streaming batch unification with log-based systems like Kafka and the topic as an approach. They are great in terms of what they do for decoupling microservices from decoupling systems and moving data, but that's it. Yeah, I hope this addressed your question. And we are also on top of the hour, so I think we can wrap up here, Umesh. Thank you so much for joining us, for sharing your whole experience here. It was a day, basically, as I said, Yelp is one of the first adopters. There is more to come along those lines of the Streamhouse next year. But always keep in mind who was here first on Yelp and Umesh realizing all this value and betting the future of a data infrastructure for a company like Yelp to the soldiers of the Streamhouse. So yeah, thank you a lot for sharing this, man.
Thank you so much, Yanis, for having me. Pleasure. Really happy to talk to
Okay,
people like
so
folks. And you feel free to find me on LinkedIn or
yeah,
wherever.
and every
And
questions you have, yeah, just reach
yes,
out
yeah.
LinkedIn or yeah. I also I don't think there is a good place for Python stuff, but the Flu Slack channel is also there, and we also have lots of Python questions. So yeah, you can also find me there, and I hope I'm nice to see you there as well, man.
Yes. Let's see you
Okay,
there.
so
Okay.
have a great evening, morning, wherever you guys are located. Bye.
Thank you so much. Bye bye.